Okay, this mini lecture is going to look at the idea of electric fields and electric field lines. It's going to be a short, very conceptual little mini lecture on the idea of what an electric field is, how we calculate it, what its mathematical equivalent is, and then how it looks visually in representation of this idea of field lines. Now, electric fields and the understanding of electric fields depends on your understanding of an electric force. So we talked about that in a previous mini lecture, Coulomb's law in the electric force mini lecture. If you haven't looked at that one, check that one out first so you'll have a really strong understanding as we talk about this idea of electric fields. Okay, so the idea of an electric field or any field is that the presence of a particle, whether it be an electric particle in our case or a massive particle in the case of gravity, by the sheer presence of it being in a space, it influences the space around it. Now, why might we think that? Well, when we have two charged particles, we know they interact with one another. We know that through Coulomb's law and the effect, we can see them influencing each other's motion. But if I have charged particle Q and I bring another particle Q nearby, how does it know? Why does it feel something just by the presence of the big Q, that charged particle Q I first referenced? That's the idea of a field. The big particle Q, so I'm going to use charged particle Q, and I'll say it's positively charged for the first part of this, is influencing that space around it, such that if I bring in a test particle, let's say small q, and we'll say it's positive 2, that test particle is going to be influenced by the sheer presence of big Q. And we know it is through that force interaction. It's going to feel a repulsive force. In this case, they're both positive, and little q is going to be influenced by that force. This influence we call an electric field. So the electric field of Q. So that is what we're going to call that influence that capital Q exerts in that space. Now that tells us that little q, we'll call this our test particle. So little q is our test particle. And we're going to use, by convention, we use a positive test particle when we're dealing with electric field descriptions. When I place little q into the space with big Q, it feels a force. Feels a force as the result of that electric field. So the force that little q feels is a result of the electric field of big Q. And if I brought a larger test particle in here, well, it would feel a larger force. If I brought a smaller particle, a smaller force. If I made it a negative particle, it'd feel a different direction of force. So the force itself is also dependent on little q. So the force a charged particle feels as a result of an electric field is related to the particle itself, the strength of that particle, times the electric field. Well, what's the electric field may be related to? Let's go back to Coulomb's law and remind ourselves what the force by Coulomb's law would look like on this little q. So if I recall Coulomb's law, the electric force is equal to K, Q1, Q2 over the radius squared, the distance between them. So the electric force on particle Q, we said, was Q times the electric field given by capital Q. Well, that is the electric force on my test particle, which means it must be K little q times big Q, our two charged particles, over the radius squared. Which tells me that the electric field, Q on both sides, that Q cancels, that the electric field itself is equal to K capital Q over R squared. So does that seem reasonable? Well, what should the influence of the space be dependent on? Well, if I have a large charge compared to a small charge, one might expect that the influence of the space is going to be different. A large charge is going to have a bigger influence, a larger field, than a small charge with a smaller influence or a smaller field. So our electric field is proportional to the charge by which is making that field. Similarly, the further and further and further I get away from that charged particle, capital Q, the less likely it's going to have influence over the space. And so it stands to reason that the larger the radius, the smaller the electric field. And so our electric field of a charged particle can be written as our Coulomb constant times the particle's charge itself divided by the radius squared. And that hopefully makes a little bit of sort of conceptual sense on how that space might be influenced. Okay, so that is our relationship for an electric field. But and the force by an electric field on a charged particle? This is going to be useful for us to remember as well. So what does that tell us about how this electric field looks? How can we represent it? How might we picture it? That's where we're going to get to our electric field line idea. So I'm just going to erase this so I have enough room, and we're going to put our charged particle right in the middle of the board so we have lots of room to look at it and explore it. Now, by convention, if we're going to look for the presence of an electric field, we're going to use a small test particle Q, small enough that it itself does not influence the electric field. We will get to what happens when I have multiple charges affecting a space. 2 capital Qs in nearby space. How does the field look in that case? But for now, let's imagine that I have only one, and it's positively charged. Now, by convention, like I said, we're going to take a positive test charge, and we're going to plop it in the space and look at the effect it feels as an indication of the electric field. So we're going to look at the force, because remember that the force on that test charge is equal to that test charge, which is going to be sort of small, times the electric field. So the direction of the force on that charge has to be the same as the direction, physical direction, right, left, up, down, at an angle, as the test charge itself. So we'll start with our positive charge Q. Now, if I put a test charge really close to Q, there's my test charge, little q. These are always going to be small q, and we're going to use a positive test charge. We know that the force exerted is going to be equal to the charge, little q, times the electric field at that point. And if the electric field, remember, is k times the charge itself divided by the radius squared, well, this is pretty close. So my radius is small, my electric field must be large. If my electric field is large, then my force is large. And we can represent that force with an arrow. We have a nice large force. Now, what if I take this exact same distance and I put my little test charge straight up? Well, the charge is the same, and the charged Q, the space charge, is the same, and it's the same distance, so the electric field has to be the same, so the force on that particle must be the same. And at that same distance, I get a repulsive force, positive, positive, of the same strength as the other one. Similarly, if I put it the same distance below, well, they're both positive charges, and they're both at the same radius, so I should get that charged particle feeling an electric force the outward direction as a result of that field. And similarly, on the left, I would get an electric force to the left as a result of that field. And quite frankly, anywhere along this radius, should I get a charged electric force of a certain strength relative to that radius and the charge, large charge Q. As I go further and further out, well, my direction is the same, but my strength is going to start to decrease on that electric force because the strength of my electric field has started to decrease. I'm further away. And if I go even further out, the strength of that force is going to be smaller as my radius increases, and thus a result of the electric field being smaller as my radius increases. And we see that for positive charges, if I place a positive test charge, the field lines all radiate outward, getting larger and larger in strength as we go outward. If I were to represent those field lines, these straight lines emanating from this positive charge, we'd find that along a certain radius, it has the same strength of the electric field. If I go a little further, a circle of the same strength of the electric field. And when I come to learn, that's what we refer to as equal potential lines. Electric field lines that are of the same strength. Well, what if instead of a positive charge, I had a negative charge Q? Still capital Q, but negative charge. Well, if I take my positive test charge Q, the same positive test charge, what does that positive charge experience? Well, it's a certain radius, and the electric field of negative Q is a certain size and a certain radius, and my charged particle is going to feel a force towards charge Q. Similarly, if I'm to the right of the same distance, it will feel that force towards particle Q. On the left, same thing, towards particle Q, and down below it, up towards particle Q. And if I move further away, well, I still get an inward force, but it's smaller because I'm further away from that charged particle, and the electric field with a larger radius starts to go down. And similarly, as I go further and further away, the force exerted by that field gets smaller and smaller. And so for a negative charge particle, the electric field lines point inward. Again, at a specific distance, they're of equal strength. The electric field is of equal strength and is going to have equal influence over that charged particle Q, test particle. And so similarly, we are going to have these areas, these lines, this radius of equal potential, equal strength of the electric field. And for negative particles, those electric field lines point in. So how do we really represent that? I have been drawing those force arrows on my picture to represent the force that test particle feels at a certain distance away from the particle Q that is influencing the space. Oftentimes, we will see these represented as simply radiating lines, such that the electric field caused by a positive point charge radiates outward. And we keep in mind that the strength of that field gets less and less and less the further we go from our point charge. Similarly, I erased the whole thing. For a negative charge, how does it influence the space? Well, we represent that negative charge influencing the space such as the electric field lines point inward. And again, the closer we get to the charge, the stronger the field. The further away, the least strong the field, the lesser the field. So we represent electric field lines on point charges as radiating out for positive charges and in for negative charges. And we can deduce that based on our understanding of how a charged particle, test particle Q, would experience a force. So that's all great for independent point charges, but what if we have two charges in the same space? How do the field lines, how is the space influenced with two charges in the same space? Well, similar to how a charged particle experiences a force in the presence of multiple charges, the electric field is impacted through that superposition idea of multiple fields. So the fields add together vectorially. Now, how does that look pictorially? Well, we can do that conceptually, again, with our test charges. And we'll just look at two examples. One where we have that positive charge Q in close proximity to a negative charge Q. Oops. And we'll also explore the field lines of a positive charge Q conceptually in close proximity to another positive charge Q. If we imagine for a positive charge, we know that the field lines are moving outward. For a negative charge, they're moving inward. And we find that the field lines for a positive charge and a negative charge all curve inward towards, you can imagine it gets bigger and bigger from that positive to that negative. Why might that be? Well, let's take that test charge Q. If I were to put a test charge Q smack dab here in the middle, well, it feels like positive force from the positive charge, force to the right. It feels a negative force from the negative charge, that's attractive, also the force to the right. So the force, the net force exerted on this test particle Q is to the right. If I looked at the sum of the electric field lines, then the force on Q would be Q times the net electric field at that point, which we can visualize is also pointing to the right. So our electric field lines go from this positive charge towards this negative charge. They're coming in at the negative and they're going out at the positive, such that anywhere along this line, the direction of that field line is consistent with both the positive charge Q and the negative charge Q. What if I had two positives or maybe two negatives? Well, let's imagine, we know that for positive charges, the field lines go outward. They're going to go outward for both of them. And so on the outside, if I put a test charge on the outside of these two charged particles, well, that test positive charge is going to feel that force to the right, and the field line is pointing to the right. It's also going to feel a rightward force by this charge along that same field line. But what happens in the middle? So that field line is accurately represented. So what happens in the middle? Well, let's say I put a test particle right smack dab in the middle. Same problem we did with our dipole, our positive and our negative. Well, if I put a positive charge, test charge, in this location, it feels a force to the right due to the electric field of this charge, and it feels a force to the left due to the electric field from this charge. So if it's feeling force to the left and a force to the right, and I'm equidistant from these two equal charges, well, the net force then is going to be zero. If the net force is zero, then the charge is non-zero, then the electric field at that point has to be zero. If I get a little bit closer to one of those two charges, does it experience a net force? Well, now my test particle is closer to positive Q, so the force is larger than the force it would feel from this positive Q on the left side. And therefore, it would feel a force. The net force would not be zero. And we see that the electric field lines split along that center. These arrows are not so great. Such that right along a very specific line, there is no electric field. The electric field is 0 because those two electric fields are going to sum to 0 and no force will be felt by that test particle. So we can kind of conceptually describe what happens to the electric field and visualize those electric field lines of two identical particles. If I were to increase one strength, one side, so if right side positive Q was larger, well, those electric field lines would be a little bit stronger. And the shape of my spreading out is going to look different. So we can represent the electric field mathematically. My understanding is relationship to both the particle that's influencing the space around it, capital Q, and where relative to that particle we are, R squared. A test particle is going to feel a force from that electric field. So that force is equal to the strength of that test charge times the strength of that electric field. And when I superimpose two point particles within the same space, the idea of superposition takes over, and we add those two electric fields vectorially, and we can conceptualize it thinking about how that charged particle would behave, that test particle, if I plopped it in there somewhere. As I add more and more test particles, as I add more and more charges that influence the space, we start to change the shape of those electric fields. And as I get multiple particles, a ring of charge or a wall of charge, we need to imagine that those are individual charged particles very, very close together. And we can examine superposition, sum of all of these electric fields together to obtain a description of that electric field. All right, so that's for a later time when we do the more mathematical. This is more of a conceptual introduction to the idea of electric fields and electric field lines. All right, good job.